Hello everyone, welcome to a new video on electromagnetic fields. In today's video, we are going to discuss about a basic law which governs the electrodynamic fields. So that is Faraday's law. So the main objective of this topic is to understand the core concepts of electromagnetic induction and its diverse applications and technologies. So we are going to discuss about how Faraday's law rules the electrodynamic fields in day-to-day activities, and also at the end of the video the students can able to explain accurately about how EMF is induced with the help of Faraday's law. So before starting into the law, let's have a small demonstration of Faraday's law. Let's take a coil of wire and connect it to the multimeter and place a bar magnet besides the coil. Now move the magnet in and out of the coil as shown in the figure and connect the multimeter. What you will observe? Do you observe any reading in the multimeter? Yes, definitely. The multimeter will show some readings, and if you connect any galvanometer, it will show deflections, which means that there is some flow of energy. So after observing this phenomena, it is found that there is some sort of energy or force which is called as EMF is being induced in the circuit. That is the basics of Faraday's law. So as per Faraday's law, whenever the rate of change of flux occurs, an EMF is induced, which is mathematically given by E is equal to minus d phi by dt, where E is the induced EMF and d phi by dt is the rate of change of magnetic flux. Now why we have a negative sign here? Because as per the Lenz law, the negative sign indicates the direction of the induced EMF. Because as per Lenz law, it states that the induced EMF will always opposes the source. So it will flow in the direction of opposite to the source. So let's define the law in detail. Faraday's law of electromagnetic induction, it states that the changing magnetic flux through a coil of wire induces an electromagnetic force in that coil, and that magnitude of the induced EMF will be directly proportional to the rate of change of flux in the circuit. So it is mathematically expressed as E is proportional to minus d phi by dt. When we remove the proportionality, we need to introduce a constant, which is EMF is equal to minus N d phi by dt, where N is the number of turns of the coil and the EMF induced is pictorially represented here. So while moving the magnet near the coils to and fro, there is an induced EMF which is found through the galvanometer. So it is the basic law of electromagnetism predicting how a magnetic field will interact with an electric circuit to produce an electromagnetic pole. So this electrical and magnetic field interaction resulted in an electromotive force. This is the fundamental operating principle of transformers, inductors, and any types of electrical motors, generators, and solenoids. So wherever you find power flow, definitely there will be an EMF. So this is how it has been simulated. When the magnet is, we have connected a magnet and a coil, and it is being connected to the CRO through a Hall probe. So whenever there is a movement in the magnets or the coil, you have to make any one alternating. So either the coil has to move or the magnetic field has to move. So when you move it, you can observe the voltage. When you move it to and fro, when the rate of change of flux is maximum, the wave also reaches its maximum, and when it is moved far away, the EMF drops. So thereby you get a sine wave which is being simulated. Let's connect it with a real-time case study. First, Discuss how wireless charging technology leverages electromagnetic induction to power devices without direct contact. So now the wireless charges devices runs with the help of Faraday's law. Now think about transformers, how it uses mutual induction to step up or step down voltage in power transmission lines. There also you can find electromagnetic induction, Faraday's law. And in induction cooktops, it directly produces heat through the induced eddy currents, right? So these are few applications, real-time applications where you can witness electromagnetic law, electromagnetic induction. Now, what is the advantage of Faraday's law? It is very cheap, easy to make the EMF to produce, highly reliable, and there are numerous factors through which you can control the induced EMF, and the EMF induced is very efficient and you can get a clean and green energy through this. The disadvantage is that to produce EMF, for example, in thermal power plants, we need to use coal and oil, which is dirty, non-renewable, hence it creates pollutions. And also by producing EMF through nuclear power plants, it is expensive and radioactive. When it comes to geothermal, it is clean and renewable, but you cannot expect that large amount of power from a geothermal. Now, where are these Faraday's law is applied? They are used in transformers, wherein which you can transfer power from one AC circuit to another without much loss of power. And we are using the EMF Faraday's law in induction cookwares, where a coil of copper wire is placed below a cooking container and it gets heated with the help of induced eddy currents. And in musical instruments like guitar, we have there also Faraday's law is being implemented. It have a pickup device attached to them which flows the Faraday's law of induction. So this application is not just contained with these three. You have n number of applications. The electrical motors, generators, wireless power transmissions, everything works with the help of Faraday's law. Now let's solve a numerical problem. A coil is wrapped with 200 turns of wire. So here N is 200 turns. On the perimeter of a square frame of sides 18 centimeter, the total resistance of the coil is 2 ohms. A uniform magnetic field is turned on perpendicular to the plane of the coil. So if the field changes linearly from 0 to 0.5 Weber per meter square in a time of 0.08 seconds, find the magnitude of the induced EMF and also find the magnitude and current of the current induced in the coil while field is changing. So you need to find two parameters. One is magnitude of induced EMF. So you have to find what is EMF. E is equal to what is the value, and you have to find the current value also, how much of current it produced. So they have given the coil diameters, coil area and resistance, and also they have given the number of turns. So by applying E is equal to N d phi by dt, you can get these values. The answer is given, and we have given another problem. Please note it down and solve it. The magnetic field through a coil having 200 turns and a cross-sectional area of 0.04 meter square changes from 0.1 Weber per meter square to 0.04 at a time of 0.02 seconds. Now find the induced EMF, and we know that E is equal to minus d by dt into phi can be expressed as NBA. So here minus NA into dB by dt. Here N is 200 and A is 0.04, and the flux changes from 0.1 to 0.04. Therefore dB by dt is 0.04 minus 0.1 because it changes, and the time at which it changes is 0.02. So by solving, you will get E is equal to 24 volts. So let's summarize. So in Faraday's law of electromagnetic induction, there are many laws. The first law is that magnetic flux linked with the closed circuit changes and EMF is induced, and that is what we have explained here. And we have seen about what is the second law, which is the magnitude of induced EMF is proportional to the rate of change of magnetic flux, and we have seen its mathematical representation also. Then we discussed about what is the advantage and disadvantage, and finally we discussed about applications of Faraday's law, and finally we saw the simulation of Faraday's law, and finally we have solved few problems regarding Faraday's law. I hope through this video the Faraday's law of electromagnetic induction has been clearly explained through hands-on projects. You can try it on your own with a simple coil and a magnet at home itself, where you can witness Faraday's law. So thanks for listening. We'll meet you in the next topic in the electromagnetic field series. Thanks for listening.